Ну, начинаем. So, first of all, I would like to welcome everybody on our lecture on neutrino physics. And I would like to recall the main, what we have discussed in our previous lectures. Yeah? So, we are considering the effect of neutrino mixing and oscillation. So, neutrino mixing and oscillations. So, we have been forced just to incorporate, to introduce these phenomena under the pressure of very strong facts from astrophysics and on detection of neutrinos from fluxes of neutrinos from the sun, from atmosphere, and this idea was then confirmed in interpretation, in analysis of results of neutrino measurements, neutrino flux measurements in different laboratory experiments from different sources. So this is what we have been obliged to include in addition to what we have in the standard model, where the mass of neutrino is exactly 0. And there is no mixing, no oscillations. Okay, what is the main, our proposals and guesses to realize these ideas of mixing and oscillations? We consider neutrino phenomena within, as I call it, dualistic way. So first, we introduce the mass states of neutrinos. We just call it the mass states. We know there are different 3 types of neutrinos and corresponding 3 mass states for which we introduce the masses. Well defined, and for these neutrinos we can rise and solve the problem of propagation. These particular neutrino fields are governed by the Dirac equation. Yeah? So sometimes this state is called propagation states. This is the Dirac equation in vacuum for neutrinos, the wave function of neutrino. This is evolution in empty space. Yeah? This is, we use this notation, known for you. This is momentum, yeah? Okay? So, there is an alternative view, but for these neutrinos we do not know how they interact with other particles. In other words, the Lagrangian of interaction of the standard model, but we would like to be as close as possible to the standard model, not to ruin the whole structure, etc. And in the standard model, we have to incorporate another neutrinos that accounts and interaction and communication with our particles. So, and there is this flavour neutrino state. This is mass states, and this is a flavour neutrino states. Neutrino states. We just determine F equals to lacton, according to the present knowledge and understanding, tau neutrinos. And these particular neutrinos participate in interaction, and they enter as a field in the Lagrangian of the standard model. Not these neutrinos, but this. And also, these neutrinos are not accessible for the problem of propagation, because they have no masses. And this is a result of our preliminary guess that 2 different visions, 2 different approaches to description of this very complicated, not usual phenomena, as neutrinos are, we should combine all together. And we introduce the mixing. So all flavor neutrinos are the mixtures of the mass states and vice versa. That was what we postulated by hands, by the way, in order to have ability to solve the solar and atmospheric neutrino problem. Yeah? So we introduce the mixing. Neutrino mixing. Well, I will just now make our calculations and all formulas simpler, and we shall consider 2 mass states and 2 flavor states for simplicity, to make all our formulas to be short. So and in case of 2 neutrinos, we can parameterize the mixing. We can introduce the mixing matrix U, and parameterize it in this following way with only one free parameter. For convenience, it can be chosen as an angle. Cosine theta. Theta is the mixing angle, minus sine theta, cosine theta. And as a result of our guesses or postulates, we have the following, that all flavor neutrinos, including electron neutrinos, is a combination of neutrino mass m cosine theta plus neutrino mass 2 sine theta. And the similar decomposition of another flavor neutrino. This is orthogonal states. Nu e, nu mu is orthogonal. Nu 1 and nu 2 is also orthogonal states. Nu 1 minus nu 1 sine theta plus nu 2 cosine theta. This is what we discussed last time. This is the idea, implementation of idea, mixing and oscillations. Now, knowing these 2 main features of different types of neutrinos, flavor and mass states, we, using our abilities, our knowledge, we can consider this like a typical quantum mechanical problem, and we can calculate the probability of conversion of one neutrino flavor to another one, if we again postulate the evolution equation for the mass states of neutrinos. We can do this again because we know the equation of motion for these neutrinos. And we postulate that equation of evolution of mass states is the Schrödinger-like equation with the corresponding Hamiltonian, and we also suppose that neutrinos are relativistic particles. We know how energy and momentum are related for each mass state. So, and we postulate the Hamiltonian of mass states of evolution is given by the energy of these 2 neutrinos, and we consider relativistic neutrinos, alpha, we consider 2 neutrino case. This is the momentum of neutrino squared plus neutrino energy mass. Okay. So then we consider relativistic neutrinos. We write that this is modulus of momentum plus 1 divided by 2 m alpha squared divided by modulus of momentum plus, and we just confine only these 2 terms. And we also suppose that neutrinos are relativistic, and the energy is more or less equal to momentum, and evolution in space corresponds to evolution in time for relativistic bodies. Yeah. Okay. Then we derive the Hamiltonian of evolution, Hamiltonian of evolution of flavor neutrino states using the relation between mass and flavor states, and using the introduced real expression of mixing matrix, using this exact expression for mixing matrix. And then we calculate the probability to observe, to detect neutrino flavor F in the initial neutrino flux composed of electrons. This is a typical problem that usually is rising when you consider neutrino flux from the sun. Most of neutrinos are produced as electron species. They just arrive to the detector, you remember, and only 1/3 of the expected number of electron neutrinos are detected on the Earth, depending, of course, on the energy band, because if you just move, depends on the energy, but in the range of about 1 MeV, it's about 1/3 part. So, and the probability to observe or to oscillate as a function of the distance, we just make these calculations, equals to sine squared double theta multiplied by sine squared delta m squared divided by 4 energies. So where we introduce the second important parameter of oscillations and mixing and oscillations as the mass square difference. In our case of 2 neutrinos, it is equal to m2 squared minus m mass square difference. Mass square difference. So there are 2 key parameters that determine the oscillation probability, and that is the end of amplification of the idea of mixing and oscillations. All these were proposed, I would like to recall, by Bruno Maximovich Pontokorva, in 1957. Then this idea of mixing and oscillations, Pontokorva at that time, it was known only, confirmed and known the existence of 2 types of neutrinos and antineutrinos. And Pontokorva in 1957, he considered exactly 2 types of neutrinos and antineutrinos. Then after the discovery of the second type of neutrino that was discovered in 1962, this idea was used by Japanese group, Maki, Nakagawa, and Sakata group. They include mixing between 2 other types of neutrinos, electron and muon, 2 flavor neutrinos, but they include only mixing. Only mixing, not oscillations. So they do not push this bubble of mixed neutrinos in space and time. They do not put it on a car or the train and move it from the source to the detector. And at that time, there was no analytical expressions that we have reproduced in the previous lecture, and as I recall you. At that time, there was not known that it is possible in such a simple way to describe effect of oscillations. And there were only words by Pontecorva, who just by words explain what will happen if there is mixing. If you recall, I told you that he just proposed that if neutrino is a mixed object composed of neutrinos and antineutrinos, then after a certain distance from the source, you will see, an experimentalist will see, or the theoretist will suppose that there will be equal mixtures of different types of neutrinos. But this is a result of mixing and averaging over time, you see. Yeah? If you just wait for a long time or just travel a long distance, enough distance, in respect to characteristic length or time of oscillations, the states, neutrinos, will be distributed in equal amount in two states. It's a typical quantum mechanical feature. Yeah? And he proposed, he just give an answer, what will happen if there is oscillations. But then Pontecorva and Gribov in 1969, they calculate probability of oscillations. They calculate probability of oscillation, more or less what they obtain, more or less this formula. Probably, maybe I'm not exactly remember, they missed 1/2 or something, but nevertheless, they put the same arguments and get this sign, they just, they derive for survival probability, but the oscillation probability equals 1 minus survival probability, obviously. So this is what I would like to recall. This is what I would like to recall. What we can say finally about the obtained probability. The obtained probability. Well, so oscillation probability, oscillation length. This is the argument of what is staying under the second sign. L equals to 4 pi energy of neutrino divided by mass square difference. This is the oscillation length. Yeah? And what is also important, if delta m squared equals to mass second squared mass first squared tends to 0, there is no oscillations, obviously. Yeah? No oscillations. So from here we can conclude that m2 cannot be simultaneously equal to 0 and m1 cannot be 0. The two masses cannot be simultaneously 0. And also they cannot be equal to each other. Yeah? So, and if you just include the third neutrino, and if you remember, I told you that there will be possibility to simultaneously explain the problem of atmospheric and solar neutrinos, using again two neutrino prescription, but with other mixing angles, different mixing angles, and different mass square differences. Yeah? If you have 3 neutrinos, there will be only 2 independent mass square differences. One corresponds to the solution, provide the solution for the solar neutrino problem, and another one provide the solution for atmospheric neutrino problem. Yeah? Okay. So this is more or less what we discussed on our previous lecture, and I would like to go further and to discuss a more general case. Of course, we know that now there are 3 types of neutrinos, 3 neutrinos. So there are neutrino electron, neutrino muon, neutrino tau, that interact and corresponds in Lagrangian of standard model integration to electrons, muons, and tau leptons. Yeah, this is what we have in the Lagrangian. We have diagrams of this type, so like electron, like muon neutrino, and this is charge, this is W boson, yeah. So, and the same diagrams for the case of muons and muon neutrinos, W boson, okay, and the same diagram for tau. So this gives insight how to measure these neutrinos in the detector. If neutrinos of the particular flavor arrive to the detector, and you would like to check whether this particular neutrino arrived, you should see and look, detect corresponding charged leptons. This is the indication of that neutrinos of particular flavor type arrive. Well, and of course, mass states, nu1, nu2, nu3, with corresponding masses m1, m2, m3. And these neutrinos, for these neutrinos we can write the equation of motion, alpha equals 1, 2, 3. We know how they propagate. And now let's consider the problem of mixing and oscillations. Mixing and oscillations of three neutrino, mixing and oscillations. Of three neutrinos. Okay? Mixing and oscillation of three neutrinos. And let's again consider more or less a realistic model of an experiment. And let's suppose that neutrino is born at a particular flavor state at x, this is a coordinate equal to 0 at initial moment t, 0, as neutrino of a particular flavor, nu f. A particular flavor. F can be whether electron, muon, or tau. This is a realistic situation when neutrino is produced in the source. Then we can decompose on each particular moment flavor neutrino in mass states using the mixing matrix for each particular space-time point. Yeah? And also we can write that at a certain moment at x and t, we can write that the flavor type of neutrino first we include the effect of propagation of mass states. We use the plane wave approximation, and also we incorporate the effect of mixing. Yeah? And as a result of these ideas, we can write for in the particular point x and t not equal to 0, we can write that this is the sum of mass states. I will just indicate this is the sum of mass states. I stands for the mass states. Mass states. From 1 to 3, in our particular case, this is the mixing matrix, Fi. This is the mixing matrix. And then we consider that neutrinos propagates as a plane waves with a particular energy and momentum, mass states of neutrinos, because we can consider the propagation in space and time only for the mass states of neutrinos. Our flavor neutrinos is superposition of the mass states. So they propagate this mass state with a particular energy, I energy I, T, exponent plus I, Pi, X. We suppose that this is one-dimensional problem and neutrino propagate along X direction. And here, this is the particular state, mass state. Yeah? This is what we will have if we suppose that each flavor state is superposition of mass states, and if the plane wave approximation is valid for description of propagation of the mass states in space and time. This is very natural. By the way, I haven't mentioned sometimes when also I was studying many years ago, dozens of years ago, the basics of neutrino mixing oscillations. I just come across a quite puzzling question. We suppose that neutrinos are relativistic, but then we use Schrödinger-like equation as evolution. Just it is possible to exaggerate and ask her, why you use non-relativistic equation for description of the relativistic objects? No, the answer is very simple. Because this is evolution equation. This is not evolution, not equation of motion. And you just choose the evolution in a form that also corresponds to equation of motion for a relativistic object. Because the Hamiltonian of evolution, we use the relativistic relation between energy and momentum. So there's nothing to do with non-relativistic approach. This is like a kid's question, yeah? Okay. This is like a remark. So, and here we also should recall that there is a relativistic relation between energy and momentum for each neutrino mass states. Yeah, relativistic energy. Yeah. Okay. So, in addition to this, we also can observe that each mass state is a superposition of flavor state. Yeah, because we can the mass states are mixed states, and also the flavor states are mixed states. Yeah, so each mass state can be expressed as a superposition of flavor states. K indicate the flavor states. Again, the same matrix, U, K, I, I, and here is the flavor states. Flavor states, yeah? Then we can express these flavor states in the first expression using this definition of mass states, using this definition and relation between mass states and flavor states. Just include, just put it by hand. What we shall have, can I move? Okay. So, and as a result, we shall have the following, that the flavor state in a particular space and time, xt, will be expressed in terms of two sums. One sum k this is a flavour index. Then the sum over the mass index. Two mathematics. We should be very careful writing these indices. UKI, UFI. Two exponents, E minus I, energy over T, plus, multiplied by plus E pi x. And here we put new k. New k. And just on this point, if to go further, two prescriptions can be used. At first sight, it seems that they are quite different. You rather could suppose, and include in your subsequent calculations, that two energies of two neutrinos are equal, or, on the contrary, two momentas of two different neutrinos are equal. The first approach is called or termed the equal energy prescription, and the second one equal momentum prescription. But the result will be the same. Okay? So, equal energy prescription. Or equal momentum prescription. So, two identical in respect to the final result for probability of neutrino mixing and oscillation prescriptions. From the point of view consideration, they're quite different. And many years ago, it was quite a wide discussion which of these prescriptions are more natural and more closely related to a real nature of mixing and oscillation. But from my point of view, this discussion was, in a wide sense, was an academic discussion, I should say. Well, so what are the differences? What are the differences? So in one prescription, we use the decomposition of particular momentum that is the square root of energy squared minus mass squared. That is energy minus 1 divided by 2 mi squared divided by energy. And in another prescription, we should expand the energy squared, that is equal to pi minus plus 1/2 momentum squared divided, oh my, I'm sorry, mass squared, yeah? Here I just simplify our relations and the expressions. I just use the simplified notation, yeah? Okay, and just using these two prescriptions, we can get different expressions from the first approach, yeah, for these exponents, yeah. Let's write this. For the first type of relation and prescription, yeah. So minus I energy I t plus I di x equals 2. So we expand now energy, expand first using this, yeah, relation, and we can get that this is minus I pi t plus I minus also, yeah, minus pi m I squared plus I pi x equals 2. Minus I mi squared divided by pi and also 2 in the denominator t. And if we consider equal momentum prescription, this is what we just indicate 2, then we shall get that this is minus I mi squared divided by 2 modulus of momentum multiplied by t. Okay, this is for realization of the equal momenta prescription. Yeah. So if we consider what we shall have in the first approach, that is equal energy prescription, then we can again expand the same I energy I multiplied by t plus I pi x equals 2 minus I energy I t, and then we expand momenta using this expression here, plus I e t minus 1/2 mi squared divided by energy I equals to 1/2 minus 1/2 mi squared divided by energy, and here we use the equal energy prescription, and we get that this is minus 1/2 I mi squared divided by 2, not 2 without 2, energy multiplied by t. Here I also should put t. Okay, this is some exercise, very simple, with in realization of two prescriptions, whether energy or momentum equal prescriptions. The difference is simile. And now we can go further. Okay? And we can write the probability of conversion or oscillations. One type of neutrino to another type of neutrino. And also we shall use the 3 neutrino case, then we shall consider more general F transition to L, where F and L can be whether electron, muon, or tau. Okay? So we consider the most general realistic case when we have 3 mass states and 3 flavor neutrino states. And we can write the probability and just use the simplified expressions. So neutrino flavor F, neutrino flavor L. What will happen with the neutrino of flavor F? And we are interested what is the probability of conversion of oscillations. Conversion as a result of oscillations from neutrino of type F to neutrino of type L. F and L are flavors, because we produce and we know what type of neutrino in flavor basis is produced and what type of neutrino is detected also in flavor basis, because the production and detection processes deals with flavor neutrinos. And we can write that this is, according to quantum mechanics, I should say, this is a square of the amplitude of transition between F and L states. And we have just derived a general expression, what happens with a particular flavor neutrino when this neutrino conglomerate travel in space and time. And we know now what we should write here. Yeah? So this is a modulus. If you remember, there were 2 sums over flavor. Again, I just recall this is flavor index. Then there is a sum over mass states and 2 mixing matrices, elements of 2 matrices, KAI U F flavor I. Yeah? Then we write the exponent minus I divided by 2, mass of squared of mass neutrino, Pi, and here this is neutrino of flavor L, and this is neutrino of flavor K squared. This is the result of using the very well-known agreement or rules of quantum mechanics to calculate the probability of transition from one state to another state. This is proportional that is given by the amplitude of transition, and we just write the most general expression for this amplitude. By the way, this is due to the fact that different flavor states are orthogonal to each other, as well as the mass states orthogonal. This is nothing but delta Lk, and we can just easily make one of these summations using this, and we get that this is the modulus sum over mass states now, yeah, mass states, mass mixing matrix Li, mixing matrix Fi, exponent minus Ai, 1/2, mass of neutrino squared divided to momentum, T, modulus. So, now we make some, squared of course, yeah, squared. Make some rearrangements just to make it more easily, more accessible for understanding and for calculations. That can be expressed as a double sum, G sum I. Here we just write 4 mixing elements of different elements of. This is 2 matrices squared, so it will be. You can make equal expression for this, but one have to be very accurate with indices. Li, Fi, L the second J, F, J. Okay? And here, what is in the exponent also doubled in the following way: minus I divided by 2, mi squared divided by pi minus mj squared divided by pj. Okay? And if we just introduce the very well known for us, the mass square difference, we just introduce this delta m squared Ej equal to me squared minus mg squared. Then we can go further and write in the following way: the sum over j, the sum over I, the mass matrix L, I, U, F, I, U, L, J, U, F, J, exponent minus I divided by 2 mass square difference squared divided by momentum I, J indices T. Or if we use another prescription, the energy equal energy prescription, now we are working in the momentum prescription, equal momentum, will be the same, but the exponent will have the following expression: I divided by 2 mass square difference I J squared divided by energy T. Okay? Yeah.
Why does the scalar production between nu L and nu K equals delta when nu L is a flavor, but nu K is a
No, L and K are flavor, both. L and K are both flavor. Here, if you remember, first we expand the initial flavor state in mass states. And then we include the opposite expression, re-expression. Then the mass state re-expressed in the flavor state. And that's why we have 2 indices that describe particular flavor states. But the flavor states with different flavors, they are orthogonal by definition.
Okay.
Thank you. So we use twice the relation between mass and flavor states, but in different directions, you see. With flavor, we expand in mass states, and when these mass states, we re-expand in flavor states. And finally, we get that in the left and right-hand side of our amplitude are flavor states. And this is done so because we have to operate in the emission point and the detection point with flavor neutrinos, because we know we can observe, we can produce flavor neutrinos and also can observe flavour neutrinos. Okay. So we can go ahead and again decompose this expression in a more simple way for the further analysis. This is the first sum that account only terms when I, the mass states, equal to J. We just take only part of these terms. When I equal to J, so that will be 0. The exponent will give 1. So, and we shall have U Li squared U Fj Fi, because J is equal to I, yeah, squared, yeah, and the doubled sum for on I less than J, and here we again have 4 elements of mixing matrix with the following indices: Li, U, Fi, U, L, I, U, L, J. Okay? Multiply by cosine double pi T divided by tau ij. So I use this the well-known relation that cosine equals to exponent plus I phi plus exponent minus double cosine, yeah? And also we introduce this tau ij, the characteristic time, ij equal to 2 pi's 2 momenta divided by mass square difference delta m I j squared modulus. Okay? So this is when we use the momentum, equal momentum prescription. Yeah? If we do the same, but within other prescription, the energy momentum prescription, equal energy prescription, then we shall have the same, but instead of this cosine, I just only write in case of energy, equal energy prescription. We have the same, but cosine will be expressed as cosine 2 pi's, 2 energies divided but by mass square difference J modulus. Yeah? No, I would like to, this is not correct. Cosine 2 pi's x, that's what I have in mind to write. And we introduce the length of oscillations. This is Lij equal to what I have just written. 2 pi's 2 momentous divided by modulus of mass wave difference squared. Okay, this is the oscillation length. This is an oscillation length. Okay. Now let's turn to the more pragmatic question. How to use these general academic formulas, I should say, how to use to interpret a real experiment. For instance, real experiment with, for example, with solar neutrinos. That is I just recall this notation, nu with this ring with a dot inside indicates the neutrino from the sun, or solar neutrinos. So the point is that neutrinos are produced not in one very narrow region of the sun. They are produced in the inner part of the sun that is about 10% of the radius of the sun. It means that we do not exactly know from which point neutrino travel to the detector. This is the point. So in order to use these idealistic formulas, the first step to use them, we should average over the distance neutrino travel, because really we do not know. We are detecting many neutrinos, the flux of neutrinos, and each of the neutrinos in general travels its particular distance. So in order to use these formulas, we should average over the distance or over time. Yeah. So what is measured or observed? What is measured is an average value. Is the average value of the probability, and we just indicate it in the following way. This is the average over time, f to L, as a function of time over t, some quite long period of time. Yeah? This is a realistic situation, and this has the following analytical expression: 1 over t, the integral from 0 to this particular t of the derived probability of flavour oscillations as a function of time over t. So, and now we just should insert here two terms that we have just derived on the previous page. Yeah? That is out of screen now. Yeah? So there will be the first term, sum over I, u squared Li, u squared Fi, plus, this is not dependent on time, obviously, yeah? And then the term that really depends on time, through the cosine function, yeah? Time or x entering the second term through cosine. Okay, plus 1 divided by 2, 0 t sum I, and I do not want to write what is here, in the limit t to infinity. Obviously, this term washes out because a particular dependence on running time through this cosine. Yeah? So we get the following, that for interpretation of realistic experiment with detection of subtle neutrinos, we should use only the first term that survives due to physical condition of the experiment of production and detection of neutrinos in this case. U squared Fi. This is very, very, very interesting result. And so what we can see, the first conclusion, everything 100% depends only on the mixing, on the elements of the mixing matrix. Yeah? Dependence on mixing matrix. Then, what is also very important, no dependence on mass square difference. A remarkable thing, yeah? And obviously, this is valid only if there is mixing and only if there is oscillations. It means that it doesn't depend on the mass square difference, but it reflects the fact that it should be non-zero mass square difference. You understand, yeah? That it doesn't depend, but you cannot put here the mass square difference equal to 0. Because in other all calculations will be 0, yeah, all formulas in the beginning, yeah. So it doesn't depend, but it will be 0 if the mass square difference are 0, yeah. This is a kind of paradox. But of course, we just include the notion that the masses are not 0. Okay. Well, this is very, very interesting, very particular feature of oscillations. And especially when we are trying to interpret results for particular experiment, very important experiments such as the subneutrino experiments. And just using this notion, sometimes I ask students to make consideration themselves and like a problem. But probably we can do it here or next time. So the problem. Suppose there are n flavor neutrinos. So F equal to 1, 2, etc. up to n. And also there are n mass states of neutrinos, mass neutrinos. This is flavor mass neutrinos, I. Yeah? Where I equal to 1, 2, etc. again n. We should confine ourselves with the equal number of mass states and flavor states, yeah, obviously. And the question is, I just formulated it in the following way. What to find, what is the maximal degree of suppression of initial flavor neutrino, after the neutrino flux travel a certain distance. Or this can be put in brackets, because in fact it doesn't depend, the question doesn't depend on the distance. It can be formulated in a more short way. What is the maximal degree of suppression of the particular flavor neutrinos if you have n flavor neutrinos, n mass states neutrinos, and arbitrary mixing? Because we have just a moment ago fixed our attention to the fact, the result we obtained, that in the real experiment, the probability doesn't depend on the mass square difference. It only depends on the way how neutrinos mix to each other. It depends on the mixing. So the problem is to find the optimal values or the optimal structure, if you wish, of the mixing matrix that provide you the maximal possible suppression in case of n neutrinos in flavor states and n neutrino in mass states. And the solution is unique. It depends on n. And I would like to ask you whether to think, or probably just we can solve it, or probably we can just leave it for the next time. I think that probably I will ask you to think about. I would like to address to your knowledge to the first year mathematical analysis course. One should consider the conditional extremum of a functional. And I would just recall, this is in the first year textbook of Ilyin Pozniak, I don't remember which. The condition of this Lagrangian coefficients. You have formulate the condition for extremum, also incorporate the relation condition between these three parameters that are the elements of the mixing matrix, and just find the minimum of this of this functional. Then you determine these Lagrangian coefficients that give the unique value for the parameters of the mixing matrix. And I can give you an answer. The maximal suppression equal to 1 over n. So if you have two species, the maximal, it doesn't depend what distance between travels. The maximal possible maximum is 1/2. If you have three species, the maximal possible is 1/3, 1 divided by 3. And if you remember, I just several times stressed that the first observation of neutrino fluxes by Davis, he got a Nobel Prize, and some neutrino flux was detected in his series of experiments in the middle of 60s of the last century. He gave a result 1/3. The suppression of Sala neutrino electron Sala neutrinos, according to results of experiments that were done by Davis, was 1/3. So it exactly corresponds to the fact that there are 3 mass states and 3 flavor states. That is the end of the game, yeah? Okay, please try to solve this, and next time probably I will help you. Okay. Well, probably you have some questions, and well, thank you very much for your attention. Yeah?